In this section of lessons, students discover the factors that determine how much kinetic energy an object has. Since all vehicles need an energy source to get them moving, they'll understand why different vehicles use different amounts of energy. We'll be using this image of two trucks that hit a power pole. One is a truck hauling bricks, and the other isn't hauling anything, yet the empty truck caused the power pole to fall down. How can that be? Students are going to make a physical model of this situation using marbles and a cardboard ramp. The rolling marble represents the moving truck, and the plastic cup that we call the energy-catching igloo represents the telephone pole. It's the target of the energy transfer, and it gets damaged different amounts by the trucks. In this case, we measure the amount of damage by the distance that the igloo moved. We can use a bigger marble and compare damage. So how does this work? Energy is often defined as the ability to do work. I like to also call it the ability to cause damage. But the formal definition of work is force times distance. With our middle school students, we're often good just saying to them that we're going to use the distance that the marble travels as our measure of energy, a proxy for energy. But let me convince you teachers that this is legitimate. The work is done against the friction force, which stays relatively constant for the igloo throughout the trials. That means that the energy is just proportional to the distance. We begin lesson 5.6 by looking at our unit roadmap. Today we're zooming in on the two trucks. How are they similar and how are they different? What would happen if each one ran into a telephone pole? Which would cause more damage? We then show our phenomenon where the lighter truck caused more damage. That means we have to become crime scene investigators to figure out what happened. Students will brainstorm what they know about energy and come up with a definition, and then figure out how we can measure it. Finally, students start planning their own investigation to figure out our truck damage mystery. In 5.7, we start by comparing different size marbles to figure out how much energy they have. A worksheet helps scaffold the investigation as students work to develop a claim that answers the question, what is the relationship between mass and kinetic energy? Their claims might take the form, when the truck's mass is heavier, its energy will be. And as we add the evidence and the reasoning, we of course find that bigger marbles cause more damage, but that doesn't yet explain our mystery, where the empty truck actually caused more damage. That motivates us to investigate the effect of speed on kinetic energy in Lesson 8. Now this investigation mirrors our mass investigation, but we keep the same marble and vary the ramp height. It's great to give students practice at repeating a similar investigation, but some of our teachers assign half the groups to investigate speed and half to do mass in order to save time. In the speed investigation, we end up with a claim like, when the truck's speed is faster, its energy will be greater. In Lesson 5.9, students graph the data that they had from their investigation with both the mass and speed on the handout. They share the graphs with the class. Why didn't every group get exactly the same result? Are there common trends that we can see across all the groups? Well, we see that kinetic energy definitely depends upon speed and mass. We basically discovered the kinetic energy equation. Both of these factors are important, so we're going to multiply them together. And linear factors are going to show up as straight lines, and ones that are going up higher at like a quadratic are going to show up with the squareds in them. Now, if you actually record the speed using slow motion video, you can definitely see this quadratic shape. But if you do what our curriculum says, which is to use the ramp height, the number of textbooks, as your measure for speed to simplify things, you'll probably end up with just two straight lines, and you won't quite capture all the details of the scientifically accepted kinetic energy equation. So you'll have to explain to students that if they had actually measured speed, they'd end up with a kinetic energy equation that looks like this. Well, speaking of speed, next up we'll look at how friction slows things down with some drag racers.